Okay, Corning and GlobalFoundries, you've announced fairly recently a collaboration, I think, to develop detachable fiber connector solutions for GlobalFoundries Photonics, silicon photonics platform. I suppose to start with, be good to understand the significance of this partnership when it comes to next gen optical connectivity. I guess we're talking or looking at AI data centers in particular.
Yeah, for sure. So I guess CPO is at the center a lot of that, like it's the key enabling technology here, and that requires optical fibers to be coupled to photonic ICs or PICs, and there's a lot of key challenges in achieving this reliably, in high performance, and at scale. So the collaboration that was announced is significant because it aims to enable very precise fiber-to-chip connections at scale by two leading companies in the CPO ecosystem. So GlobalFoundries makes the silicon-based photonic ICs, and Corning makes the optical fibers and all the connectivity that goes with it. So that's in that sense, it's an important collaboration.
Okay, in terms of drilling down some of the technical whatever the word is, I'm sorry, so the technical parts to the solution. I think you're leveraging a glass waveguide based edge coupler, which is compatible with the Photonics V grooves. Would it be good to understand how the technology improves performance compared to certainly to traditional optical interconnects?
Sure. So I'll break this down a little bit. When you say glass waveguide based edge coupler, there are two elements of that. One is the glass waveguide piece, and then the other one is the edge coupling piece. So I'll talk about those two just a little differently. We'll start with the edge coupling piece, and there are different ways to couple a fiber to a chip. You can do this using an edge couple mechanism. You can do this using a vertically coupled mechanism that typically uses grating couplers in the silicon. Or you can also couple using evanescent coupling techniques. So there's different ways to do it. And the two that are the most common would be edge and vertical coupling or grating coupling. And now different chipset OEMs will use either one according to the pros and cons that suit them the most. So specifically in terms of edge coupling, it tends to be a little bit higher performance in terms of minimizing insertion loss in the coupling between the fiber and the chip. However, it requires tighter alignment tolerances. So therefore, a key advantage of edge coupling mechanism is that you will typically get better performance out of it, but it's a little bit more challenging to put together. So that's one part of the question that touches on edge coupling. The other part of the question is on the glass waveguide piece. And just to be precise here, I mean, an optical fiber is in essence a long glass waveguide. But here what we're talking about is a short piece of glass with multiple waveguides that are inscribed on it. And one of the advantages of this type of technology versus a more conventional fiber array unit approach is that you can achieve very, very high density right at the edge of the photonic IC. Much higher density in terms of bringing the waveguides much closer together than you could, even with the thinnest of fibers. So that's certainly one advantage. And the other advantage as well is that these waveguides are inscribed on the glass substrate by means of the lithographic process. And so the waveguides are very, very precisely placed on the piece of glass, and you don't need to deal with individual fibers, if you will, in a fiber array unit or directly on a PIC. So there's also some advantages in terms of getting already very, very precisely placed waveguides as you interface with the photonic IC. So hopefully that answers the question a little bit in terms of what are some of the key advantages of this approach.
Yeah, no, that's great. Thanks. And as I think we referenced at the start of the conversation, co-package optics increasingly important when it comes to high density AI workloads. In terms of your own detachable fiber connector approach, how does that support co-packaged photonics? And I guess in particular the advantages it brings in terms of scale up and scale out networks.
Right, right. Well, so as I mentioned earlier, CPO requires fibers to be tightly coupled to their corresponding waveguides on the PIC. And so now these fibers can be permanently attached, as is the case today with pluggable optics, also used in data centers. But we can also couple these fibers in a way which is attachable and detachable. So think of it as a fiber to chip connector. And so this then allows the optical engines or the photonic ICs within the optical engines to be assembled, without, dealing with a bunch of dangling fibers in the process, right? So basically that leads to simplified assembly of the optical engines. And this is beneficial for CPO in general, whether it's for scale out or for scale up. But I think one advantage of using a glass substrate based approach is that we expect there's going to be further simplification of assembly at very high scale, and which is what is expected to be required for scale up architectures. So we believe that this type of technology will start to make a lot of sense for the very, very high density that can be achieved at the PIC, along with the very high degree of scale that's going to be needed for scale-up type of applications.
Okay, and in terms of your own the company's expertise when it comes to ultra precise fiber alignment, I think that's you sort of highlight that as being important to
Right.
this solution. And it'd be good to understand how that sort of expertise helps reduce insertion loss, but and also improving power efficiency, I guess, is one of the big focuses when it comes to AI and the high
That's right.
performance compute data centers. Yeah.
Yeah, that's right. So with traditional FAU or fiber array unit structures, which Corning also provides, it's important for each individual fiber to be very precisely aligned with their corresponding waveguides in silicon. So imagine, a linear array of 40 fibers with a core pitch or distance between adjacent cores of around 127 micron. So there's a lot of fibers to align very, very precisely with their corresponding waveguides onto the photonic IC. Now, it turns out that the fiber geometries are not perfect. In other words, they're not perfectly around. The core is not perfectly centered, all the time. So there are always tolerances. And there's an accumulation of these when you're dealing with a high number of fibers. And so all it takes is a little bit of misalignment with some fibers and their corresponding cores so that it's going to be a lossy connection, right? In other words, light is going to be lost in the process, and that would lead to a higher insertion loss, which ultimately leads to increased power consumption that's going to be needed to compensate for that. So Corning can make exceptionally good fibers in terms of physical geometries. And we can also make exceptionally good glass V-grooves in an FAU chip or in an FAU substrate. And so together, that leads to much more precise core pitch tolerance in terms of smaller variation in the distance from core to core, both in the Y and X directions. And that will in turn lead to much improved loss performance, i.e. lower loss, which ultimately translates to improved power consumption. So the concept of a photonic grade optical connections to the chip becomes really important to be able to maximize performance.
Okay, and in terms of what else you are, I think, working on, obviously we talked a little bit about the edge coupled solutions, but I think you're also developing vertically coupled
Right.
detachable fiber to PIC options. guess it'd be good to understand there in terms of offering multiple coupling mechanisms gives flexibility for the network folks and I guess the data center operators as well.
Yep. Yeah, absolutely. And over the years, Corning has worked on different types of coupling mechanism. I mentioned even evanescent coupling at the very beginning. It's not commonly used today, but we've done a lot of work on this. And what is really commonly used right now is both edge coupling and vertically coupled. So, and as I mentioned earlier, like different chipset OEMs are going to favor different types of coupling mechanism according to the pros and cons that suit them best. So vertically coupled structures are in demand as well. And so, as I mentioned earlier, one of the benefits of that approach is that it requires less precision tolerance than you do with edge coupling, but you might get a little bit of a hit performance-wise. That really depends on the design. And so either way, whether it's edge coupling or vertically coupled structures, a lot of fibers are required to be coupled to the photonic IC, and Corning is actively working on different types of fiber to chip coupling mechanism, whether it's edge coupled or vertically coupled solutions. And with GlobalFoundries, we're working on different types of approaches as well to suit basically the broad range of chipset OEMs for CPU applications.
Okay, and as I think you've already mentioned, GlobalFoundries, they're bringing the high volume silicon photonics manufacturing capabilities to the collaboration. In terms
Yeah.
of how combining what they are doing with Corning's optical technology, how does that help enable scalability for the AI and the machine learning workloads?
Right. Well, so first of all, I think you've mentioned it. Like scale is hugely important for CPO, given the very, very rapid evolution of AI learning models. And that is in terms of the server capabilities and switching capabilities, and also optical port speeds. So these are all evolving very, very rapidly. And the optical infrastructure that's needed to support all this includes optical fibers and cables, very high density optical connectors, and fiber to chip connections. And Corning already has the global scale to support that growth. And so does GlobalFoundries. So scale is important in terms of being able to provide the required density and the required architectures. And these are evolving extremely rapidly. And so scale in terms of being able to bring the innovations, and scale in terms of being able to just scale up in terms of operations are absolutely essential. And we both already have the scale to do that, and so that's another reasons why this collaboration is of importance.
And for the networking professionals, the collaboration, what does it mean in terms of whether it's future optical interconnect standards or more generally the evolution of high bandwidth data center infrastructure?
Yeah, it's a good question. For networking professionals, here is that an important consequence of this types of architecture and technology is that the data center optical network is expanding inside the equipment. So these networks then are no longer designed strictly from front plate of equipment to front plate of equipment, but truly from chip to chip. Right, so there's an optical network inside the boxes and outside the boxes, and they seamlessly interact with each other. So I think that's a significance here, is that these optical networks are now becoming end-to-end chip-to-chip networks, whether this is chip to chip, within a rack, or between racks, or across data centers. And so I think that's a real significance for networking professionals that design these optical networks. They need now to consider the extension of the optical networks inside the boxes, right to the chips.
Okay, and if I remember correctly, Glassbridge was you demonstrated at both. I think it was ECOC not too long ago, and also GlobalFoundries Technology Summit. Were there any particular key performance metrics or benefits that the folks that saw the technology sort of were excited by, focused on in terms of what caught the interest of the spectators, if you like, when it came to the demonstrations?
Right. So just to go back a little bit, even before ECOC, the concept of the glass bridge we showcased together with GlobalFoundry at OFC earlier this year, right? Was that in March or April? Now this was it was a more of a static demo to demonstrate the concept of passively aligned fiber to chip connector using glass substrate. So what was demonstrated at ECOC was kind of a similar setup, but this one had light going through it. Performance was being measured, and there were improved features in terms of passive alignment, which is a really important attribute. So you're asking about, what caught the interest of people. So there's three things I would say. The first was first of all, the performance of that connection with a detachable connector of well under 2 dB. So I think that was an important performance parameter. And then two other attributes of this demonstration generate a lot of interest. One is that the fiber to the glass bridge connection, so the actual fiber connection to all of this, was made using a standard and very mature TMT ferrule technology, which is very, very well established today. So it's not like this is a completely new form of fiber connector. So that attracted a lot of interest. And the other thing is then the glass bridge to the PIC was entirely passive. And this is difficult to achieve. And that required matching alignment features both on GlobalFoundries silicon and on Corning's glass bridge in such a way that you could passively align these two and achieve very, very tight tolerances and therefore very good insertion loss.
Excellent. Maybe just a couple more things, and we may have covered some of these already, but I'll ask anyway. AI, high performance computing workloads, clearly driving demand for faster and more power efficient connectivity. That's, I guess, the major focus. So, either sort of remind us, or if there's anything else to say in terms of how these new fiber connector solutions directly address the needs of this AI infrastructure.
Yeah, we did touch on a lot of those already. I could, summarize it by saying that precise fiber to chip connections and therefore alignment tolerances is really key here, right? The optical connections are now coming right to the chip, so making that connection in a way which is first of all detachable. It really simplifies how these systems are assembled, so that's really important. But getting good, robust connection with excellent performance, but importantly at scale. It's one thing to do this in the lab and do a few hundreds, but if you're going to do thousands of millions of those, that becomes very challenging. So I think that's what we're demonstrating here. We're demonstrating a path to get to this, and I think that this is quite significant.
Yeah, and maybe just sort of following on from that, the collaboration in terms of its contribution to the future of optical interconnects, I guess with data centers, networks, and even the semiconductor industry. So just put it in perspective, I guess.
Yeah. So as mentioned earlier, I think data center technologies and architectures are evolving very, very rapidly, and with it, so do optical connections right at the chips. And that evolution is in terms of density and performance. As I mentioned, this needs to be done at scale. And so the collaboration here between Corning and GlobalFoundries is going to bring a lot of innovation around very efficient fiber to chip connections, but so as to enable not just kind of the current generation of CPO systems, which are initially will be for switching applications, but for future generations of co-packaged solutions to enable scale up architectures, for example, where these connections are going to be expected to be increasingly dense and at much higher scale as well. So a lot of innovation to be able to enable these fiber to chip connections for multiple generations of co-packaged optics.
And perhaps finally, just on the collaboration side, I'd just be interested your thoughts. I mean, could you imagine a few years ago having this kind of collaboration, or is this a sign of the way the industry is moving that into the future to address the complexities of much of the IT infrastructure required for AI? I guess there's no one sort of organization can do everything, so you do have to
That's
start
true.
with that.
Absolutely. It's a broad ecosystem, and there's a lot of innovation that needs to happen at every layer of the ecosystem. So I think this absolutely must be the case. I mean, this is one collaboration. There's other collaborations that Corning is doing as well. Other collaborations with other ecosystem players are making as well. And sure, standards are moving forward as well. But I think we're going to see a lot of those collaborations between key companies in that supply chain, if you will, at every layer of the ecosystem in order to enable those type of solutions, right? And I think one of the challenges as well, beyond the challenge of technology, is the ecosystem in itself. Because moving away from pluggable optics that has a very, very well established sort of technology roadmap, if you will, over many years now, but also a very well established supply chain mechanism, is now changing somewhat. Some of these systems are becoming, more vertically integrated. There's a lot of optimization that can be achieved that way at a system level, and that requires changes in the supply chain as well. And the only way for that to happen is with key players to collaborate closely together, and to enable these advances in technology to be realized in an ecosystem sort of way. Hopefully that answers your question.
Yeah, no, that's great. I mean, it's been fantastic to chat, and thank you so much for sharing so many great insights into the collaboration, what's going on. It's obviously a fast-moving, complicated scenario, but it's yeah, very exciting times, I'm sure. And thank you so
Yes.
much for your time, Benoit. Thank you.
All right. You're very welcome. Thank you.